Okay, welcome to Chemistry 111. Right now I'm going to go through Test 2 for fall 2020. So, in case you don't have a chance to be there in lecture, this is Test 1 in 2020. So here is what we got. So starting out with question 1. Question 1, the following information to answer the following 2 questions. Standard microwave oven produces a 2.45 gigahertz frequency. 2.45 gigahertz frequency. So new is 2.45. What is the wavelength that a microwave oven uses in millimeters? So we want to go from frequency to wavelength in millimeters. So to do this, you have our C equals lambda nu. And C is a constant at 2.998 times 10 to the 8th meters per second. One thing we have to note is that 1 hertz is equal to 1 inverse second. So we have to turn gigahertz into hertz. Now, to do this, we have hertz, kilohertz, megahertz, gigahertz. So gigahertz is 10 to the 9th hertz. So how did I do that? 2.5 GHz and 1 GHz. There is 10 to the 9th HC, which is equal to 2.45 10 to the 9th gigahertz, or 2.45 times 10 to the 9th inverse seconds. So the next thing is converting this in finding wavelength. So we're going to say C over nu equals lambda. So 2.998 times 10 to the 8th meters in a second divided by 2.45 times 10 to the 9th 1 over seconds equals our value in meters. 8 divided by, here where you have to make sure, you want to make sure you put this whole thing in parentheses or use the E functionality so that you make sure you're dividing by 10 to the 9th. So in meters, we get 0.112 meters. But the question asks in millimeters, so the last step to get the full credit in this fill in the blank type question is, so in 1 meter there is 1,000 millimeters. So the correct answer is 122 millimeters. 122 millimeters. Question 2. Question 2. How many joules would that wavelength produce? Joules would that wavelength produce? Okay. Now you can leave the frequency and do this. Energy equals H nu, where H is 6.626 times 10 to the negative 34th joule seconds. So we have to use this value to do this. So you're going to do 6.626 times 10 to the negative 34th JS times 2.45 times 10 to the 9th inverse S, and that will give us energy. X26 times 10 negative 34th times 2.45, 10 to the positive 9th. Should get a number that's really small. That is fine. The number you get is 1.62 times 10 to the negative 24th joules. So really small. But keep in mind, it's a microwave. Light typically is in 10 to the 19th. Visible light is 10 to the 19th. So a microwave, which is weaker than visible light, should be weaker than that. And that is indeed the case. Looking at problem 3. What is the full electron configuration of the element gallium? This one you need both full electron configuration, and you need to find where gallium is. Gallium is element number 31. It's element number 31, right after zinc. So, full electron configuration. So that means it's row 4. Row 4. All the other rows are standard. So 2 elements in the first row, 1s2. 8 elements in the second row, 2s2, 2p6. I'm working my way across the 8 elements in this third row, 3s2, 3p6. Now we're into row 4. Starting with elements, potassium and calcium, that's 4s2. Then I'm working my way across. I get into the D. It's D something, but D is row -1, so it's not 4D, but 3D. There's 10 elements in the D, so 3D10. Gallium is the first element in the P row. So, my pen suddenly die all of a sudden. It appears it has. So, we go back to 4. 4p1. First element in the P. So, there we go. How my pen's working again? 4p1. So that would be the correct answer for problem 3. Problem 4, a multiple choice problem. Which of the following ions would be isoelectronic with calcium? So calcium 2+, calcium 2+. We want isoelectronic, which means calcium is element number 20. So 20 protons. Now, because it is 2+, 2+ means it's going to be 20 minus 18. So we want something that also has 18 electrons. Titanium would be 22. But and it's also 2+, but it would have 20 electrons. So no, that's not isoelectronic. We have strontium, which is in the same column as calcium, but it's element 38. So that would also not be isoelectronic, because that would be 36 electrons. Even though it would have the same electron configuration setup, it is not truly isoelectronic. And then finally, we have chlorine, which is element number 17. So if it's chlorine 1-, it would be 1- would be from 17 to 18. The chlorine being 17 minus 18 would give us the 1 minus. So the correct answer is chlorine. Bromine 1 minus is element 35. So no. So we want chlorine. Chlorine is the correct answer. Chlorine 1 minus. Now describe in your own words the ionization energy trend both throughout the group and across a period. So ionization energy goes down as we go down the table. Decreases, and as we go across the table, ionization energy goes up. So basically, ionization energy decreases as size increases. Increases due to electrons further away, further from nucleus. Ionization energy increases as attraction increases and distance from nucleus decreases. So that's pretty straightforward trend. I'm not asking you for explaining the exceptions. I'm just saying the generalized trend. Okay. Your number 6. Which of the following would be the correct condensed electron configuration for the element Tallium? So let's look up Tallium. Ta. What element is Tallium? Tallium is 73, which means it's row 6. Row 6. So to do a condensed electron configuration, we need the there's a typo in here, but that's fine. We need the previous row to be described as a noble gas. So the first thing we do is we need xenon. Xenon is the last element at the start of row 5. That's our row 5 noble gas. So that means B prime, or essentially that should be C, is wrong. It doesn't have xenon. Then to start off, you should start off with your 6s2. Don't forget your 6s2. As we start off with our cesium barium. Now here's the tricky part. We jump down to F. We jump down to F. As we jump down to F, we have to go through our F's, so F14. Well, as we jump down through F's, it's row -2 for F. So it's not 6F, it's not 5F, it is 4F14. And then we move our way back to our D's, and Tallium is under the third group in the transition metal. So it's row -1, so it's 5D. And then third element, so 5D3. So the correct answer is answer D. Xenon, 6s2, 4f14, 5d3. Okay, use the following energy level diagram to answer the following 2 questions. This is when I increase the size, that's what caused this goof. So I'm going to go ahead and flip lower down and redraw this. So redraw this right over here. 1s, 2s, 2p, 3s, 3p, 4s. Let's see. I'm losing my pen again. Three D. 1, 2, 3, and then 4p. Okay. Answer the following two questions. For the element sulfur, how many electrons are in its valence shell? So sulfur is element number 16. 16. Let's put electrons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So remember, the valence shell is only the outermost layer. Typically, we count it as the S and the P. S and the P. So 1, 2, 3, 4, 5, 6. How many electrons? 6 valence electrons. How many of those valence electrons are unpaired? So if you did this right, it's just these two. So 2 unpaired electrons. If you did it wrong, well, yeah. Name 2 ions that would have the electron configuration 1s2, 2s2, 2p6. So really, anything that is isoelectronic with neon, that is equal to neon. So what 2 ions are isoelectronic to neon? And this could be anything. You could have put N3 minus. You could put O2 minus. You could put F1 minus. You could put, let's see, next one, sodium plus 1. You could say magnesium 2 plus. You could say aluminum 3 plus. You could put carbon 4 minus. All of these are isoelectronic. You just have to name any 2 ions. You could say silicon 4 plus. You could keep going, but those are probably the outer limits of what you might get. But any of those would be isoelectronic with neon. Okay. Write the condensed electron configuration of titanium 2 plus. Titanium, so this one's extra hard because it's not titanium, it's titanium 2 plus. So start off, let's do titanium because you want to at least do that right. 22. It's element 22. So let's start with the full electron configuration to make sure we understand this. Then we're going to go to the condensed. Then we're going to go to titanium 2 plus. So that means it's row 4. 1s2. 2s2, 2p6, 3s2, 3p6. Here's row 4, 4s2, 3d2. All the way, row 3 is argon. So the condensed electron configuration for titanium is argon, 4s2, 3d2. That's just titanium neutral, titanium 0. Now titanium 2 plus, so we lose, when we lose electrons, we lose from the P and then the S and then the D. So if we're losing 2 plus, titanium 2 plus, we are going to lose from the S before we lose from the D. So we're going to say argon 3D2. And that's all we have to say. Argon 3D2. And that is the condensed electron configuration for titanium 2 plus ion. Okay, number 11. As always, I typically like to give at least one lab problem. Lab problems aren't supposed to be hard. If you came to lab, it should be pretty straightforward. During the properties of light lab, we learned absorbance can be modeled by Beer's law. If luminol had an extinction coefficient of 7, so epsilon of 7636 at 347 nanometers, what concentration must be present if the absorbance is 0.894? Cuvette is 1 centimeter. So B is 1. So the equation is A equals ABC, or epsilon beta C. So with that in mind, we say 0.894 equals 7636 times 1 times our concentration. Remember, we do not use the wavelength anywhere in this equation. I know it's tricky. 894, we do not need it. In all actuality, absorbance and molar absorptivity depend entirely on the wavelength, but they are not represented in this equation in any way, shape, or form. So your concentration must be equal to 0.000117, or you could say 1.17 times 10 to the negative 4th m. Either of those values would be correct. Now, what would the condensed electron configuration of phosphorus be? So phosphorus, P, that is element number 15. That is row 3. So once again, I'm going to start with the full and go to the condensed. So the full would be 1s2, 2s2, 2p6, 3s2, the third element into the p, so 3p3. Now the condensed 1s2, 2s2, 2p6 is neon. So we neon 3s2, 3p6. That's 3p3. So I start with the full, and then maybe I work through my condensed. Do you have to do it that way? No, but I'm just doing it and showing the practice. How do I do that? Now, which of the following elements is likely to have the following ionization energies? So we have 787, 1577. We have 3,231. We have 4,356. We got 16,091. 19,784. And 23,783. So what we're looking for is a huge jump. A jump that is greater than a doubling or greater than a tripling, greater than an increase by the lowest number. Whatever, take your starting number. Now, when you add either that or 2 times that to your previous number, if you're close to the energy, it's just a normal loss. So 787, just looking at that, 787. If I double that, it's about 1574. So that's about 2 times increase. 787 times by 3. It's a little bit more than the increase, 2361. We'll say 787 times 4. That's a little bit closer. So it just about doubled from 2 to 3. Now 787 times 5. Well, let's say 787 times 6. So this is between 5 times and 5 times and 6 times the present, and then 6. Then you see but that one went up by about 1,000. That one went up by about a little bit under 1,000, a little bit over 1,000. What about 1691 divided by 787? There's about 2 times. There's about 4 times. There's about 5.5 times. This is about 20.5 times greater. We see a huge jump after 1 loss, 2 loss, 3 losses, 4 losses. See a huge jump at loss 5. This is loss 5. So what does that mean? Loss 5 would be the loss of a noble gas electron. We can easily lose 4 electrons without worrying about the loss and loss 5. So which element would be in the 4th group, meaning it does not want to lose the 5th electron? Which is the 4th group? Be silicon. Silicon is the fourth element. It would be in the 4A column. It can lose 4 electrons without losing before it has a huge jump. So okay, back to a proper math problem. If the energy of the average medical X-ray is something like 1.60217 times 10 to the negative 15th joules, what would the wavelength be? So this one, we're taking energy and going to lambda. Please note, ask for wavelength. Wavelength. Don't be tripped up. So start, I'll say E equals H nu. So I can say E divided by H is equal to nu, and then go from there. So 1.60217 times 10 to the negative 15th divided by 6.626 10 to the negative 34th. This should be a reasonably big number. 1.60217 6.626 10 root negative 34th. The frequency is 2.418 times 10 to the 18th. Please note, that happens to be answer B. But, and this is a big but, I do not ask for the frequency. I ask for the wavelength. So, gotta keep going. Gotta keep going. Next thing, you go C equals lambda nu. So you're going to say C over nu is equal to lambda. So you're going to say 2.998 times 10 to the 8th divided by 2.418 times 10 to the 18th. So 2.998 times 10 root 8 divided by my big number, 2.418, 10 root 18. You get a number that looks like 1.224 times 10 to the negative 10th meters. If you're following your units, 1.24 times 10 to the negative 10th meters. So we have to go which one of these is closest to that number? That's 1.24 times 10 to the positive ninth meters. So no. Got to remember, millimeters, there's 1,000 millimeters in a meter. There's 10 to the 6th micrometers in a meter, and there's 10 to the ninth nanometers in a meter. So which one of these is the correct answer? If you convert them to each unit, you'll find out that answer A is the correct answer. 0.124 nanometers. Okay. In your own words, describe the p orbital, the shape of the p orbital. It's not too hard. P orbital is one of the more normal one. P orbital is the one that looks like, you could say, a bow tie. It looks like a figure eight. It looks like a dumbbell, infinity symbol, something like that. There's 3 different versions of it, all in the one-dimensional axis, either x-axis, the y-axis, or the z-axis. All of those things could be added, but let's say dumbbell, figure eight, something like that. 16, number 16. Using electron energy diagram from above, how many electrons would be unpaired in the element iron? So I'm going to redraw my energy diagram. 1s, 2s, 2p, 3s, 3p, 4s. I thought out of room like a schlub. So I'm going to do 3D down here, but it should be above. 2, 3, 2, 3, 4, 5, and then 4p. So elemental iron is element number 26. 26 electrons. And elemental iron. So putting in 26 electrons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Okay, 21, 22, 23, 24, 25, 26. So how many of them are unpaired? 1, 2, 3, 4. 4 unpaired electrons. 4 unpaired electrons in element iron. Write the full electron configuration of lead. Ooh, this is a fun one. By fun, I mean incredibly long and tedious. Element number 82 on row 6. So that means it has a lot to go in it. So looking at this. Rows mean so 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, because row minus 1, 4p6. Repeat for row 5, 5s2, 4d10, 5p6. Now we're finally on row 6, the one that actually matters. 6s2, 4f14, 5d10, and lead is 2 elements into the p. So 6p2. Please note, this is always 14. The max is 14. It's not 15, depending on where your periodic table is. Some periodic tables have trouble distinguishing that. And so if you count wrong, you'll see a 9 and a 15 instead of 14 and 10. So please note that that's how that actually should be. Last few. place the following compounds in order of increasing lattice energy. Yeah, we haven't covered this, but we will. BeO, NAF, Na2O, and MgO. So the concept here is rather simple. The lattice energy is proportional to the charge, the size of the charge of each guy divided by the distance. So size and charge. The big thing, the size is never doubles. The size is the minimal effect. But the charge always doubles if the charge changes. So the first things first is place these guys in order based on their cation and anion charges. The next thing to do is place them based on size. So looking at this, beryllium is group 2, so it's 2 plus. Oxygen is group 6, so it's 2 minus. Sodium is group 1, so it's 1 plus. Fluorine is group 7, so it's 1 minus. Sodium is group 1. Oxygen is group 6. Magnesium is group 2. Oxygen is group 2. That is 6. So right there, just looking at the charges, I can say that NAF has the lowest energy, followed by Na2O. And the next one is which one is going to be one of these two. Because we're essentially we double it, and then we quadruple it. But we have to look at the size. Magnesium is row 3. That's row 3. Beryllium is row 2. So if you compare that, the bigger size means we're dividing by a bigger number. So MgO means that's going to have to be bigger molecule than BeO, which means it has to be lower lattice energy. So row 2 for beryllium means it's much smaller and thus higher lattice energy. Because whenever you divide by a smaller number, you get a bigger result. Problem 19. In Principles of Chemistry, the nurses did a lab similar to the magnesium lab. Of course, we didn't do the magnesium lab. We did the chlorine, this lab, essentially. So I've given you this lab to try to make it a little bit easier. We did chlorate, where we did 1.575 grams of potassium chlorate. And upon heating, there was a release of the oxygen to produce 0.958 grams of potassium chloride. What mass of oxygen was released, and then what would the empirical formula be? So to figure this, you subtract these two numbers to figure out the mass of oxygen released. Not 1.575 minus 0.958. Now, in the lab, we didn't actually find the empirical formula. We just found the mass percent of oxygen. So 617 grams of oxygen. To find the empirical formula, we would take find out the moles of oxygen versus the moles of the compound. 0.617. So 0.617 grams divided by 16 moles. 16 grams per 1 mole. 617 divided by 16 is 0.0385 moles. And now let's look at KCl. We have 0.958 grams of KCl. K is 39. Cl is 35.45. So the molar mass is something like 74.45 grams per 1 mole. 0.958 divided by 74.45 means we have something like 0.01287 moles. Now, when we divide by the lower number to get the ratio of KCl to O, we should get 3856 divided by 0.12. You get a ratio that's 2.996, which is to 1, which is safely 3 to 1. So your empirical formula should be KClO3. Then finally, essentially number 20, place the following atoms in order of decreasing atomic radii. So we have Li, we have F, we have Ca, we have Ga. Now let's look at this. That's two different trends, placing them based on column and row. Gallium is row 3. Row 4, my bad. Calcium is row 4. Fluorine is row 2. Lithium is row 2. So as we move across the table, size decreases. But as we move down the table, size increases. So the biggest one would probably be calcium, followed by perhaps gallium, then lithium, and fluorine. However, if you had a size chart, you could actually compare. So this one's kind of a little tricky one, kind of hard one. Maybe these two guys are switched. Kind of hard to say without actually looking at some numbers. Decreasing. And finally, okay, no, we still got, oh, good Lord, okay. Let's see, what do I have for you? There's, okay, no, I do not have the size chart. Okay, so we got quite a few problems here. 21, write the condensed electron configuration for iodine. Iodine is element number 53. So doing the hat, which is row 5. So once again, I'll do the full, then the condensed. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6. Now I'm on row 5, the row that actually matters. 5s2, 4d10, 5p5. So the condensed electron configuration would have to use krypton to represent row 4. Krypton, 5s2, 4d10, 5p5. That would be the condensed electron configuration for iodine. Write the condensed electron configuration for tin, 2+. So once again, write the full, then write it condensed, and then make it charged. Tin is row 5, element 50. It's 50 on row 5. So 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6. Now on row 5. 5s2, 4d10, 5p2 would be the neutral tin. So abbreviating as krypton, 5s2, 4d10, 5p2. That's just tin 0. So tin 2+, we take away from the p first. So it's krypton, 5s2 4d10. And that's what it is. Place the following isoelectronic series in order of increasing size. So if they're isoelectronic, the more negative it is, the bigger it is. The more negative it is, the bigger it is. The more positive it is, the smaller it is. So strontium 2 plus is the smallest, followed by rubidium plus 1, followed by bromine 1 minus, followed by selenium 2 minus. Straightforward. Last two ones before the bonus. Which of the following group would be characterized with 8 valence electrons and its highest principal energy level and unwillingness to make any bonds? So 8 valence electrons, S&P, doesn't want to make any bonds. That's a noble gas. That is in column 18 or column 8A. That's the noble gas electron configuration. Finally, Mackenzie police use the radio channels 37.4 megahertz. What is the energy generated by this radio wave? Once again, you have to turn megahertz into hertz before you can find energy. In 1 megahertz, there is 10 to the 6th hertz. So you get 3.74 10 to the 7th hertz, which is 3.74 times 10 to the 7th inverse seconds. E equals h nu. So we're going to say 6.626 times 10 to the negative 34th times 3.74 10 to the 7th inverse seconds. When we do that, 6.626 times 10 to the negative 34th times 3.74 10 to the 7th means we would have 2.48 10 to the negative 26th joules. Okay. All that is the math. Bonus. Green Lantern, DC superhero, is part of the Lantern Corps, which has multiple groups of all the colors. One of the arch nemesis, Sinestro, is of the Yellow Lantern Corps. However, based on the visible light spectrum, which colors should really be his enemy? His polar opposite. What we had to do, we had to think of our lab. Our lab said our Roy G. Biv spectrum. So you say, for the circle, red, orange, yellow, green, blue, violet. So green, the polar opposite should be red. So the red lanterns should truly be the villain of the green lanterns. But c'est la vie. Scientists don't always make the comics. So that right there is what was the test 2. That was 25 questions. That is probably most similar to how the test would be if we took the 2-hour thing. Maybe not 25 questions, but you see there's a lot of fill in the blanks and places for partial credit. So that is a good day. Hopefully this is useful for the people who need it.